Welcome to ChemDoodle Shorts. I'm Mary, your ChemDoodle Pro. Let's learn about Lewis dot structures and octet rule exceptions. Lewis dot structures utilize chemical symbols and dots to depict covalent bonds and non-bonding electrons in atoms or molecules. They can help to determine a molecule's geometry and are also handy when demonstrating organic reactivity and mechanisms. You've learned how to draw Lewis dot structures with atoms such as carbon, nitrogen, oxygen, and the halogens. These atoms follow the octet rule, which states that an atom bonds in a manner such that its valence shell is filled with 8 electrons. However, as with any rule, there are exceptions. Let's learn more about these octet rule exceptions. You're likely already familiar with one of the exceptions, hydrogen. Methane, CH4, has a central carbon atom with 4 atoms of hydrogen bonded to it. Each single line represents 2 electrons being shared by hydrogen and carbon. With 4 single bonds, there are 2, 4, 6, 8 total valence electrons. Another way of representing Lewis dot structures is with only dots for the electrons. To create a Lewis dot structure in ChemDoodle, select the drawn molecule, then select the Structure menu, and create Lewis dot structure. In this Lewis structure, we easily see the 8 valence electrons shared between the carbon and hydrogens. Each hydrogen is happy with 2 electrons in its valence shell, instead of 8 valence electrons, like carbon. Hydrogen follows the duet rule. It only has an s orbital, no p orbital, so the maximum valence electrons it can have is 2. The duet rule also helps to explain why helium and lithium are stable with 2 valence electrons. Another octet rule exception are incomplete octets. We'll look at borane, BH3. Let's determine the total number of valence electrons. Recall that an atom's group number or column in the periodic table equals its total number of valence electrons, counting from the left of the periodic table and excluding the transition metals. Boron is in group 3, so it has 3 valence electrons. Hydrogen is in group 1, so one hydrogen atom has 1 valence electron. But remember that we have to account for 3 hydrogen atoms in borane. Adding these all together, we see that there are 6 total valence electrons in borane. With only 1 atom of boron, compared to 3 atoms of hydrogen, boron is the central atom, and 3 hydrogen atoms are bonded to it. Recall that each single bond represents 2 valence electrons, so the Lewis dot structure can also be depicted like this. Drawn in this way, we easily see that there are 2, 4, 6 valence electrons in borane, just as we calculated. Both of these Lewis dot structures are complete. While each hydrogen is stable, following the duet rule, with 2 valence electrons, boron only has 2, 4, 6 valence electrons, not 8. It has an incomplete octet, but it's stable. Other elements with incomplete octets include beryllium and aluminum. Beryllium is in group 2, so it has 2 valence electrons, which can form 2 bonds. Therefore, it tends to have 4 valence electrons in a molecule. Like boron, aluminum is in group 3, so it has 3 valence electrons, which can then form 3 bonds. So aluminum tends to have 6 valence electrons in a molecule. In contrast to incomplete octets with too few valence electrons are expanded octets, another type of octet rule exception. Expanded octets accommodate more than 8 valence electrons. Let's look at xenon tetrafluoride, XeF4. Xenon is in group 8, so it has 8 valence electrons. Fluorine is in group 7, so it has 7 valence electrons. And there are 4 atoms of fluorine in xenon tetrafluoride. Altogether, xenon tetrafluoride has 36 valence electrons. Xenon is less electronegative than fluorine, and there is only 1 atom of xenon, so xenon is the central atom. 4 atoms of fluorine are bonded to it. With 4 single bonds, each consisting of 2 electrons, we have drawn 2, 4, 6, 8 valence electrons. However, we already determined that there should be 36 valence electrons in xenon tetrafluoride. This means that there are still 28 valence electrons to be added to the Lewis dot structure. Recall that main group elements are stable with 8 electrons in the outer shell. Each fluorine currently has just 2 electrons and needs 6 more electrons for a full octet. So let's add those in, 2 at a time, as non-bonding lone pairs. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. We've added 24 more valence electrons as non-bonding lone pairs to the fluorine atoms, but there are still 4 valence electrons left to add. Where do they go? Each fluorine is stable with a single bond and its complete octet of 8 valence electrons. The fluorine atoms don't need any more electrons. When the outer atoms have a complete octet and are stable, then add any remaining valence electrons to the central atom. Let's add the remaining 4 valence electrons to the central xenon atom. Drawn in this way, we easily see that each fluorine atom has 8 valence electrons for a full octet. Xenon has 2, 4, 6, 8, 10, 12 valence electrons, an expanded octet. Hypervalency typically involves highly electronegative outer atoms and a non-metal central atom in the third period or row and beyond. Expanded octets are more common than incomplete octets. Some elements with expanded octets include phosphorus and sulfur, among others. Phosphorus has 2, 4, 6, 8, 10 valence electrons here. Sulfur has 2, 4, 6, 8, 10, 12 valence electrons here. Keep in mind that an element in the third period or beyond has the potential to expand its octet, but doesn't always. A final octet rule exception is when there is an odd number of valence electrons. Let's look at nitric oxide, NO. Nitrogen is in group 5, so it has 5 valence electrons. Oxygen is in group 6, so it has 6 valence electrons. In total, nitric oxide has 11 valence electrons, which is a bit unusual as it's an odd number. Thus far, we've only encountered molecules with an even number of total valence electrons. Let's draw the Lewis dot structure for nitric oxide. Nitrogen is bonded to oxygen with a double bond, so they each share 4 valence electrons, leaving 7 valence electrons still to be added to the Lewis dot structure. To complete oxygen's octet, let's add 4 more valence electrons as non-bonding lone pairs. 2, 4. Now there are 3 valence electrons left to add to the Lewis dot structure. Let's add these remaining valence electrons to nitrogen to help complete its octet. 2, 3. There are no valence electrons left to add. Drawn in this way, we can easily see that oxygen has 2, 4, 6, 8 valence electrons, a complete octet. Meanwhile, nitrogen has 2, 4, 6, 7 valence electrons. It's almost a complete octet. To help determine preferred Lewis dot structures, we can calculate the formal charge of the atoms. The most stable Lewis dot structure has a formal charge of 0, or as close to 0 as possible. For nitrogen, the formal charge is 0. For oxygen, the formal charge is also 0. This means that this arrangement of valence electrons with an incomplete octet and an unpaired electron on nitrogen produces the most ideal Lewis dot structure for nitric oxide. An odd number of valence electrons is an octet rule exception, but there are few stable molecules with an unpaired electron. Due to the unpaired electron, these free radicals are highly reactive. Lewis dot structures are useful representations of the valence electrons about atoms and molecules. Numerous atoms and molecules arrange themselves to form octets so that there are 8 electrons in the outer shell, but there are octet rule exceptions. These include atoms that follow the duet rule, such as hydrogen, helium, and lithium. Another exception includes atoms with an incomplete octet, having less than 8 valence electrons. These include boron, beryllium, and aluminum. In contrast to incomplete octets are expanded octets. These atoms can have more than 8 valence electrons. Some of these include sulfur, phosphorus, and xenon. A final octet rule exception includes atoms with an odd number of electrons. These atoms with an unpaired electron are highly reactive. Keep all these exceptions in mind as you draw Lewis dot structures. Thanks for watching ChemDoodle Shorts.